Well, hello guys, here Mr. G with another video. This is lesson 3 from electric circuit. So far, these 3 lessons are applicable for the grade 10 and 11. This time we're going to be talking about resistors that are connected in series and in a parallel. And it's quite important because it's the basis of all this work we are going to do. Now, we're going to start when the resistors are connected in series, and you need to know that resistors are connected in series when 2 or more resistors are connected consecutively. So they are connected consecutively end to end, and that will make us to have only one path for the current to flow. So during this connection there is only one path. The current do not split or divide in different ways. Here we have one example of a circuit in which there are 3 resistors and all of them are connected in series. If you follow the current starting from the battery, the positive side of the battery, you can see that it will follow in this direction here, guys, as I can draw there, and then it comes all the way there and it only goes straight past all these resistors and ammeter. I placed the couple of ammeters, but it's not necessarily to have all those ammeters. I just want you to show you here. So that it means that in this circuit there is only one path for the current. Now the voltmeter, even it is connected in parallel. You know voltmeters are connected in parallel. We spoke about that in a previous lesson. The current won't go through the voltmeter because the voltmeters has very high resistance. So all the current will go straight past all these resistors. That is how the current is going to flow, and you can see that there's only one pathway there. Okay, so now important here. Let's see the 3 different concepts we spoke before in each of these cases, these different let's say circuit. The first one is the resistance. Now the equivalent resistance, which is also called total resistance in a series, is going to be equal to the addition of the resistance of each resistor. As you can see here, is quite simple. So if the resistors are connected in series, like the case here, then you can calculate the total resistance in series, which is called equivalent resistance, by adding the resistor. However, guys, this one, it is given to you in the formulas. It is here in the formulas, or you need to know that this is for resistors in series. Alright, so if you have that one, you know that you can use that formula to calculate the equivalent resistance for resistors in series. You just add all of them, only when the resistors are in series. If they are not in series, you cannot use that formula. Okay, so now we're going to look at the current, which is on the right hand side here. I make the color because of the ammeters. Now the current in series is going to be the same across each resistor. So this is very important part. The current is the same. It doesn't matter the resistance of the resistor, and it doesn't matter how many resistors you have there. So the current will be the same across all the ammeters that you can see there in the circuit. Let's take off this one so you don't get confused perhaps right now. And then we're talking about A1, A2, A3, and A4. The current is the same across each of them, guys. Now there is an important red note I take here. If there are more resistors connected in series, the total current will decrease. So if the more resistors I add connected in series, the less the current will become. Alright, so that is important. And here I said the total resistance of the circuit is increased as you add more resistors. Okay, guys, if you remember the formula for current is equal to potential difference divided by resistance. You can see here that if you increase the resistance, then the current is going to increase. This one is for part of the circuit, and in this case we're talking about the series part of this circuit. So this one is regarding to current. It is quite simple. And then potential difference is the last concept we're going to be talking here. The total potential difference across all the resistors in series is equal to the sum of the potential difference across each resistor. And if you come to the circuit, you can see that there is a voltmeter measuring the potential difference of each individual resistor. And there is another voltmeter here which is measuring the total potential difference, not of the circuit, but the total potential difference for that series part of the circuit, and that is why I call it potential difference S, or potential difference for the series part of the circuit. And you need to know that the potential difference for any series part of the circuit when the resistors or any component are connected in series is going to be equal to the addition of the potential difference of those individual resistors in this case. And very important, the potential difference is greater across the resistor with greater resistance. You can see here, guys, you can see here this one, the potential difference is directly proportional to the resistance. And then important, that one is actually Ohm's law, and Ohm's law can be applied anywhere in the circuit. So if you go to the definition of resistance, resistance is equal to a potential difference divided by a current. This one can be applied anywhere in the circuit. So for example, you can apply it for the total series part, but you can also apply it for R1, and you can say R1 is equal to a V1 divided by I1. And like this one, you can also calculate certain quantities that they could ask you in any question. Or if you want for this part for Vs, you can say that Rs is equal to a Vs divided by Is. And then, guys, you can calculate the resistance in series, for instance, or the resistance for one resistor, or even the potential difference. You can always rearrange that formula. So this one is everything you need to know about the resistors that are connected in series. So now we are ready to go to the resistors connected in parallel. So when the resistors are connected in parallel, then they have all a common terminals. That is the main point here. And I said it previously, but I'm going to say it once more. These resistors are connected in parallel, not because there are three parallel lines, but because all of them have this common terminal here, as well as this common terminal here. And that is what makes them to be in parallel, guys. That is a parallel connection here. Okay? And then obvious, because it is in parallel, there will be more than one path for the current to flow. As you can see, this one is the very important part about a parallel connection. You need to know that there will be more than one path for current to flow there. You can see it here. Now, how each of the concepts behave, or how to work with each of the concepts when the resistors are connected in parallel. Let's start with the resistance. Well, we are going to calculate the resistance of the resistors connected in parallel using this formula here. This formula is the one you are going to use for resistors connected in a parallel. All right, and something important, that formula, it is given to you in the formulas that you have in the exams. You can see it here. This is for resistors in parallel. Resistors in parallel is quite important, because it's the one you are going to use when the resistors are in parallel, and it's given to you, so you don't have to struggle there. Now remember, the resistance in parallel, which is what you could be looking for here, is at the bottom, is the denominator. So when you finish any of those calculations, you need to know that the resistor in parallel, or resistance in parallel, is equal to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3, everything to the minus 1, because the resistance is the denominator. So be careful, because the formula is like that, but at the end you have to get to the power minus 1 to get the correct answer. Now, if you have only two resistors, you can use then this formula here. But as I said, if you have two resistors only, so this one is when you have two resistors. Alright, if you have 3, you cannot use it in this way. Will be another way, but I'm not going to show you all of them. I recommend you to use this one because this one doesn't matter how many resistors you have, guys, and it's quite simple. It's not that bad. All you have to do is to get to the power minus 1 at the end. Now, important, very important. If you connect more resistors in parallel, the total resistance decreases. The total resistance of the parallel part, and obviously the total resistance of the entire circuit will decrease. So this one is very important. Take note, guys. When you watch the videos, I recommend you to get a book, stop the video, take important notes, etc. Now, the current. How does the current behave in a parallel connection? Now, what is going to happen is that the current is going to split across each resistor. Now, it doesn't mean that it's going to split equally. It depends on the size of the resistance, how big the resistance of the resistor is. But it is going to split, and that is important. So current comes here, and at this point, the current is going to split. Little bit is going to go there. Let's call that one current 1. Little bit is going to split there. This is current 2. And little bit is going to split there, and this is current 3. Guys, the current will split in a parallel connection. Alright? Now, when you go to this point, all the current come back together to give you the total current once more. Alright? So that is what is going to happen. It's not split at this point because this is a voltmeter with a very high resistance. Okay? So the current split, and therefore the total current before and the total current after the connection is equal to the addition of the current of each resistor that were connected in parallel. And that is a quite important thing. You are going to use it for a lot of calculation. If there are more resistors connected in parallel, the total current will increase. Of course. If current is equal to potential difference divided by resistance, all this one is coming from the same formula we've been talking, Ohm's law. We can call it definition of resistance. It doesn't really matter how you want to call the formula, but you can see if the resistance here is going to be bigger, then the current is smaller. If the resistance is smaller, the current is bigger. And if one resistor stop working, the current will still flow, of course. If one of these resistors, any of them, breaks because it burn or something like that, the current still flow through the other 2 resistors. Not the same in series because it's only one pathway, and we didn't mention that one, but it is here in this point, and that's why I say you must stop the video and take notes. If any of those resistors burst, then the current cannot pass through, and then the circuit will stop working. But it doesn't happen when the resistors are connected in parallel. And the potential difference in a parallel circuit is the same. When I say the parallel circuit, I refer to the parallel part of this specific circuit, because most of the time you will have combination. So the total potential difference across all the resistors in parallel is the same. Guys, this is the small summary about the 3 or the 2 types of circuits we are going to be doing. Obviously, remember, there will be combination. We are going to be looking at one example I copy here for you to explain all these concepts more or less and how to use it. The examples say, consider the following current diagram, in this case supposed to say circuit diagram, where the battery has a negligible internal resistance, and calculate the following. Here is a diagram, but in this diagram the potential difference of the battery is equal to 6 volts. It's not written there, but there is given to you. Calculate the equivalent resistance of the circuit. So of the whole circuit, we have to calculate the equivalent resistance, or in other case, we're going to write external resistance. Later on, you will learn why. Now, we need to know that to calculate the external resistance of this circuit, we have to add the resistor in series, which we have the 2 ohms right here, plus the resistors in a parallel. Now, in this case, this side here is the parallel resistors. Alright, this is the resistors in parallel, but be careful because in those parallel resistors there is a series short combination there. These 2 ones here are in series. In other words, we can say that this little rs here is equal to 1 plus 5, and that is 6 ohm. That is this combination here. So we first have to calculate the resistors in parallel, which is the 3 and the 6, the combination of these two in series, so we can substitute to the external resistor there. So let's calculate the resistors in parallel. Remember that resistors in parallel is equal to 1 divided by R1 plus 1 divided by R2. So 1 divided by R in parallel is equal to 1 divided by 3 plus 1 divided by 6. Okay? And then we have that 1 divided by RP is equal to a half. Now, you have to remember that this one is the denominator. So RP is equal to 1 divided by 2 to the power minus 1, and therefore the resistors in parallel is equal to 2 ohm. 2 ohm. That is the resistor in parallel. We are going to substitute there. So we are coming back here. We have that the external resistance is equal to 2 ohm plus the resistors in parallel, which is also 2 ohm. Guys, the resistance of the external resistance is equal to 4 ohm. This one is question A. We answer question A. Quite simple. Let's go to answer question B. The current through the 2 ohm resistor. So you have to calculate the current through the 2 ohm resistor. Guys, it is quite simple. Remember, the current is the same throughout the whole circuit. So if we calculate the total current in the circuit, in actual fact, we do have the current in the 2 ohm resistor as well as the current in the parallel resistor, because the current is the same. So let's quickly calculate the current there. We're going to solve it down here for B. And then the current, we can use Ohm's law, or the definition of resistance. We're going to write it as it is in the formulas that they are going to give you in the exams. I want to use those formulas. They are the formulas, guys. Here is the definition of resistance. We are going to write it like that in the question, so we have it exactly as it is given to you. Resistance is equal to V divided by R. Divided by I, sorry. And we are going to substitute what we have. This one is going to be for the total or the external. Let's write external circuit. External circuit. Right? Later on, you will understand what I'm speaking about, external circuit. So the total resistance in the external circuit is what we have here calculated, which is 4 ohms. So here we have 4 ohms equal to potential difference, which is given to us. The external potential difference is 6 volts, so it's 6 divided by I. And when you rearrange this one, you have that I is equal to 6 divided by 4, which is equal to 1,5 amperes. This one is the current that passes the 2 ohm resistor. But remember, we learned that the current is the same throughout the circuit. So the current here, I am going to just write it here. The current here is equal to 1,5 amperes. But remember, the current through the whole parallel part, not just through the individual band, but the whole current is also going to be 1,5, which remember is going to split when it reaches this point. It's going to go part of it there and part of it to that side. This one is important for what is coming now. Calculate the current through the 1 ohm resistor. So you have to calculate the current through the 1 ohm resistor only. So how are we going to calculate this current here? Remember, the current is going to split in 2 parts. So the first thing we're going to do is we're going to calculate the current that is going to be going to the 3 ohm resistor there. And this is a little bit more calculation. So we have the current that is passing through the whole parallel connection here. We are going to get the potential difference through the whole connection D. This one is going to be question C because this is a little bit more work. So using the same formula, we are going to say R in parallel is going to be equal to potential difference in parallel divided by current in parallel. So if we substitute what we have here, guys, we have that the resistance in parallel was calculated is 2 ohms, equal to a potential difference in parallel. I'm looking for that one divided by the current, which remember is the same everywhere. I'm talking about the whole complete parallel connection as I circled there. So here is going to be divided by 1,5, and then the potential difference for the parallel connection is going to be equal to 3 volts. All right, so now because they are in parallel here, 3 volt, which is the potential difference, is going to be 3 volts for this side, and it's going to be 3 volts for the whole side down. For everything there is also 3 volts there. So using this one, we calculate the current for the 3 ohm. So I'm going to write here now, same formula. Resistor for the 3 ohm is equal to potential difference for the parallel connection, which is the same, divided by the current that passed to the 3 ohm resistor. I'm using the 3 ohm there as to understand the numbers I'm using here. So this one is 3 ohm is equal to potential difference to the parallel, which is 3 volts, divided by the current which I am looking for. So when I calculate this one, current is equal to 1 amperes. Now, what it does mean? Does it mean here? That when the current split 1 ampere went all this way, this is 1 ampere, and the rest will go that way there, which is the same. So the current now, the current that is going through the 1 ohm is going to be equal to 1,5 minus 1 ampere. This one, we're going to move it a little bit because we're working with this here. All right, so if we say that the current that is going through the 1 ohm is equal to 0,5 amperes, guys, and then that is the answer to this question. Now remember, it's 1,5 ampere for all this part here. So all this part here, we have a current, I'm going to write it here, current of 0,5 amperes. There we go. So now question D, and we are almost done. The potential difference across the 5 ohm resistor. Now guys, this is not a big problem. We already have the current through the 5 ohm resistor, which is 0,5 ampere, because it's throughout the whole little series circuit there. So for D, the potential difference is quite simple. We're going to keep using the same formula. This one is D. Now remember, I always write the formula like this because it is given like that to you in the exam, but you can rearrange if you want. It's not a big problem there. When we substitute there, we are talking about the 5 ohm resistor. So the resistance is 5 ohm. We're going to substitute it like that. Is 5 is equal to potential difference, that is what you are looking for, and the current we calculated, remember, it is 0,5 for that little circuit which is series there. It's 0,5, so it's 0,5, and when you rearrange this one and you multiply, and then you get that the potential difference is 2,5 volts, and that is the answer for that next question. Now the next one and last question of this one say the charge that flows through the 3 ohm resistor in 5 minutes. Now to calculate the charge there, we are going to use the definition of current. Let's go quickly to the formulas I want to show you. We already spoke about that, guys. Here is the formula to use to calculate the charge. We do have the current because we did calculate it previously in a previous question. It is 1 ampere, and we have the time, which is 5 minutes. You cannot work in minutes. 5 minutes is equal to 5 times 60, which is equal to 300 seconds. We have that one. We have the current, which is 1, and then we are looking for the charge. This is question E. I'm going to write it, I think it's enough space. Charge is equal to a current multiplied by time. It is given to you like this in the exam. So the current was 1 ampere and the time was 300 seconds. Therefore the charge is 300 coulomb. That is the answer for this specific question, guys. We are done with the example, we are done with the video. I hope it helped. It is a good practice for the grade 10 and 11 and the recall for the grade 12. Thank you for watching. Thumb up, subscribe for the channel. I'll see you next time. Mr. G here.